One live.
All right, good evening, everyone. So we left off kind of right in the middle of this example for transformer differential protection using a 787. We had gone through all of the settings that are in the kind of general relay setup area of the settings. The winding CT connections, the CT ratios, kind of all the basic stuff, the CT compensation settings that we knew were going to be really important, especially for our transformer differential relays. The winding voltage settings, transformer MVA rating. Now we're going to get into the specific settings for the differential element itself. So we left off on this slide. Okay. I do have a mild cold, so if I have to mute myself to cough or sneeze, or please bear with me, sorry. So now in the differential area of the settings file, we've got the following settings that we need to determine and set in the relay. Obviously, the first one's pretty simple. We're just going to enable the transformer differential element by setting E87 to Y. The tap 1 and tap 2 settings are actually automatically calculated by the relay. It uses the MVA rating, the winding voltages, the CT ratios, and the CT connection settings that we set during the last class to calculate those tap settings. What's interesting about that is, we went through an example of how to determine what those taps need to be set to for an electromechanical relay. And that this kind of takes all of that out of it, right? But you still want to understand how that works, right? That's really important. But when you actually program one of the digital relays, a lot of times those taps are calculated for you. Not every relay manufacturer is going to be that way. I've seen it where you have to calculate them yourself as well, but this relay does calculate it automatically. Then we need to set the differential operate element. And like Brandon had said a couple classes ago, as it relates to the bus differential operate quantity, and somebody asked about the safety factor and why you used 1.5 in his application. And he said, well, it goes back to the relay manufacturer and their documentation and what they recommend. And that's really what it is for transformer differential relays too. It depends on the specific make and model, and you got to read the instruction book for your relay and see what they recommend. This particular relay recommends a setting of 0.2 to 0.3 for the operate quantity. And what's important to note about this is that's in per unit. So it's actually the pickup multiplied by your particular tap. So tap 1 is for winding 1, which on our relay is connected to the high voltage delta winding, and then or if you're going to calculate it on the low side, what it is in primary or secondary amps, you would multiply by tap 2. So that's important to note. Most of the settings that you guys have dealt with, I'm sure, are set in amp secondary. This isn't an amp secondary setting. It's multiplied by the tap. And that's how you get your secondary amps or primary amps. Then we set or can set the 87AP and 87AD settings. This is actually it's not used for tripping. This would be for alarming purposes. So if your pickup was above this 87AP setting for a duration of 87 AD, this is set in seconds. If it's above that pickup for that amount of time, it'll trigger an alarm. So that's an optional setting that the book says to, basically just set that less than your operate, usually to half of your operate quantity. And this is actually a really important thing to note. Not every relay has this ability. When you hopefully Smitty will talk about this when he talks about relay testing as well. But when you go to put one of these transformer differential relays in service, bus differential relays as well, but more importantly, when you put a transformer differential relay in service, because you have the additional issue with the compensation, the winding compensation settings. If you're not doing it yourself, you just set the relay. Try and see if you can't talk to the person that's testing it and ask them to look at the operate quantities on the front panel of the relay, or dial into it if you communicate with it and figure out what the operate quantity is before they leave, because it should be 0. And if your operate quantity is the same as one of your restraints, then it's possible you've got one of these CT compensation settings wrong, or maybe they left a CT shorted in the transformer mechanism housing, or something's wrong. It should be an operate quantity of 0 when it's in service feeding load, or very low. I mean, it may be, maybe it'll on noise, it'll trickle up or whatever, but it should be essentially 0. And it can be that way and not operate because the differential is on a slope, right? So if you've got equal operate current and restraint current, and you're operating on that slope, you're down here, and it's not tripping just because there's enough restraint current to keep it from operating. But you could have a through fault, and now all of a sudden, because you've got those compensation settings incorrect, now your operate current can go above the restraint current into that operate region on your differential curve, and you can actually trip for an out of section fault. And so I've seen that happen. The first time there's a distribution fault after they put one of these transformer differential relays in service, the transformer trips, and then you go back and say, well, why didn't they catch that during testing? Ultimately, it's your responsibility to get those compensation settings right. But if you're not there, try and get somebody to take a look at it. You'd be surprised how often that, because they'll test it based on what you tell them the settings are, right? So you say it's a DY1 transformer, and they'll run the test set up for a DY1 transformer, but because of the primary phasing, it's actually DY11, say. So when they go to put it in service, everything tested right when they tested it. It's not necessarily their fault when they tested it. It's that, the physical phase shift isn't what you thought it was and programmed the relay to look at, and what they tested to, because they tested what you told them to set it to. So final in-service check, try and get those. And like I said, bus differential relays too, more importantly for these transformer differential relays, happens all the time.
Hey, Andrew, can you just expand a little bit upon, you said what you tell them to test it to? Can you tell them a little bit about how to test to the operate restraint curve, so that they kind of have a sense of, what parameters and what values that you come up with?
Well, so I don't know if I have a slide in here. I don't think I do. I went back and forth as to whether or not to put it in here, but I can pull up.
If you don't, that's okay. I was just curious, because you do have to, I did give them some multiple test points to be able to test the curve, and sometimes I've seen that you push a lot of operate current, but maybe not. So
yeah, I'm not an expert on relay testing, and what I meant by they test it to what you tell them to do I didn't mean like you give them the specific set points, but they're going to look at the relay settings and say, okay, he or she said it's a DY1 transformer, so they'll set up their current injections to match a DY1 transformer. And that's what I was trying to say, So if you had that wrong, they're going to say, well, it says DY1 here. They're not necessarily going to go look at the primary phasing and double check that DY1 setting is correct. And that's what I meant. But I guess, this is the let's see, this is the operate current. Apologize for the artistry. IOP. This is IR restraint. And it kind of looks like this usually. So it's kind of flat down here, linear region, and then you get to the slope 1, and then slope 2. And this should look very similar to what Brandon went over a couple classes ago, which is why I didn't bother to cover it again, because it's fundamentally, it's the same thing. You're looking to, in the linear region, or this in the slope 1 region, you're looking to compensate for the inaccuracies that are not transient. And what I mean by that is, like, you can have the load tap changer can change, right? So you're going to have some inherent inaccuracy in there, right? If you set your transformer taps to the selected no load tap changer position and LTC neutral, and everything should be, you know, 0 operate current. Well, then when you go to 1 raise or 1 lower, say you've changed the turns ratio of the transformer, and now you've got a little bit of operate current. So you can have LTC differences that you need to account for. And then up here is, this is the nonlinear restraint, or nonlinear slope, I should say. So this would be for preventing misoperations due to things like CT saturation. So, but in essence, it's very similar to the concept that Brandon went over for bus differential relaying. Did that answer more or less what you were looking for, Paul?
Yeah, it's just getting a bunch of points so that you're right below the curve and right above the curve.
Oh, I
Make
see
sure
what
the
you're
relay
saying. Yeah.
actually operates and restrains as it's designed. So normally the test engineer will just plug in points that the settings engineer will say, here you go, plug these in, and it's either going to operate or it's going to restrain. And that just makes sure that the relay is doing what it's supposed to. It won't take care of the phase shift necessarily, but those are some of the test points that you have to develop. Yeah, that's exactly right. Yeah.
Right. So what Paul's saying is you'll test different points along this curve to make sure that the relay operates above the curve for these points and doesn't operate for points along here. And so, like, it'll continuously ramp up the operate current or the restraint current as needed until it gets to the line, and then it'll actually, usually the test results will give you a plot, and it should look exactly like this line. It'll show you where that point is that it started to, or that it tripped, went from the restraint region to the trip region. Okay, so that was a lot to say about, you know, this is just an alarm, but I wanted to go over why one might have that in here. The restraint slopes, like I said, this is very similar to what Brandon covered for bus differential. Okay, I went too far right here. Okay, so this is talking about the first slope. So this one, this is a little bit different than bus differential because, like I said, the transformer has a different errors that, you know, steady state errors is what they call it, or proportional errors. Things like the no load tap changer position, the LTC tap changer position. You've got your relay accuracy, CT accuracy, excitation current on the transformer. You don't have that for a bus. So this is the recommendation in the 787 manual for how to determine your slope 1 setting. So like I said, you got to look at the instruction manual for your specific relay. Usually they'll have guidance in there as to how to set those slopes. Slope 2 is looking at your CT error, CT saturation under CT error under CT saturation, and trying to accommodate that. If you've done your job correctly and you've done your CT performance calculations and sized your conductors appropriately during the design phase and made it so that CT saturation isn't an issue at your location or your application, then slope 2 doesn't even really matter. You can set slope 1 and slope 2 to the same setting and just operate on a single slope characteristic. In my experience, that's usually what's done for newer installations. If you're putting a relay in to protect an older transformer and the customer or client doesn't want to replace the CT cables because there's no drawing that documents where the conduits are, and they don't know where it is, and they just want to reuse what's there. You do your CT saturation calculations and find out that, you know, the CTs could saturate. Then you may need that second slope. So this is the guidance from SEL on how to set the slope to setting. We also want to set, or we'll often have to set, an instantaneous unrestrained element. So this is to cover faults that are inside the transformer and where you have operate current that's so high that you don't want to wait for the restraint calculation to determine a trip. So just very heavy current levels. SEL recommends that you set the pickup approximately 8 to 10 times your tap setting. And you can double check to make sure that you have enough fault current to reach that level, but that's just their recommendation. So this disregards that differential slope and just operates immediately just on the operate current. Second harmonic blocking. This is also different than bus differential protection because we don't have these blocking or restraint options. So transformer inrush can contain a substantial amount of second harmonics. So I don't know, the amount that it can contain is, you know, it's kind of magic. Obviously it's not, right? There's a science into it, but it depends on the transformer configuration, like whether it's a three-legged transformer or four-legged. That all goes into what the restraint needs to be. In general, in practice, usually you make kind of assumptions and kind of general safety factors on these things, either recommended by the instruction manufacturer, the relay manufacturer, or the client standards. Schweitzer says that 15% blocking is usually sufficient for security purposes. So what this is trying to do is prevent nuisance tripping. When you go to energize the transformer and you get this, you get the initial inrush of the magnetization current into the transformer to get the flux going in the core, you've got that fundamental frequency current, and you've got your second harmonic current as well that kind of adds on top of that. Because that second harmonic current only occurs, or primarily occurs, during inrush, if you have a certain percentage of your operate current as second harmonic current, then the differential element will block you from operating because it's inrush, or presuming that it's inrush. If you didn't have this, many older electromechanical relays don't have this, obviously, then there were instances where you energize the transformer and the transformer differential relay tripped and you wouldn't know why. So it's just a nuisance because now you've got this lockout relay rolled and you go, okay, well, is the transformer failed? And maybe you have to take it apart or run some testing on it to make sure that it's okay before you re-energize it. And that's not fun. Nobody wants to do that. So that's the purpose of this second harmonic blocking. Fourth harmonics are the same thing. The even harmonics are primarily associated with inrush, the second, fourth, and sixth harmonics. So again, you can set your fourth harmonic blocking. Then you have fifth harmonic blocking, which is associated with overexcitation of the transformer. And overexcitation occurs when you basically over voltage the transformer windings, because you're trying to force more flux through the core than the core is capable of handling. So that's the overexcitation. So when you have that situation, you get fifth harmonic current. And this is a way to prevent you from tripping your transformer differential relay during overexcitation. So again, you might get an overvoltage issue because I don't know, I guess. Well, give me an example, Paul. Can you come up with an example of why you might get an overvoltage condition? I can't really think of a good one.
On the secondary?
On the primary.
Oh, primary, okay. So you're talking essentially about a volts per hertz condition. It would probably be during energization where maybe the grid has got too low of a frequency. Because it's really DPDT, you need that frequency to be 60 hertz to get to DPDT, and if you're pushing the voltage, it's so I would imagine it's under, like if you were connected to a generating station or for some reason, and the frequency output was too low. I can't imagine why. I think it's usually more a problem with the frequency than the voltage, because most of these times these transformers are maybe 106 per unit or something like that. But I've never seen a volts per hertz trip except for when it was connected to a generator that was trying to start up, and it tripped because the generator still wasn't, it was at 50 hertz. So there's no generator circuit breaker. It was just rolling up slowly, and they were trying to push it too fast. And then that was the problem. That's the only time I can think of.
SEL just recommends a setting of about 35% for your fifth harmonic blocking. So if your client is inclined, or if your relay manufacturer recommends a certain setting, then in general, that's what you go with.
And can I just add, Andrew, the harmonic blocking is a huge deal, because I worked on a project where a 666 MVA transformer tripped because a GE relay used 2 out of 3 harmonic blocking. You had to have 2 out of 3. The Schweitzer only used 1 out of 3, and it was energized, but the GE tripped the unit offline, and that was a huge, I mean, when you get that, that's a NERC issue or an ISO issue. So harmonic blocking is an essential thing to prevent nuisance trips.
You said it was when it was initially energized. It was
no, it had run for 10 years, and then just one of those times where, because it needed 2 out of 3 blocking, the GE relay only had a 1 out of 3, and the Schweitzer blocked it, but the GE didn't, because it needed 2 out of 3, and it was the second phase was just below the 20%. I think the setting was. So
was it a through fault or something?
No, it was just energizing. They had energized.
Oh, they were energizing it. Okay,
they were energizing. Okay. It wasn't a problem. It was actually, it should have blocked operation.
Yeah. Right. Yep. Then we determine, do you want to enable the restraint or blocking? And then you say yes or no. And that's it. Now you've set up your transformer differential protection, at least for this particular relay. So, okay, next, most common form of protection for transformers is transformer overcurrent protection, which is usually it's just used as a backup to the transformer differential protection. It's either in the same relay or a separate relay, or sometimes both. You have high voltage winding or high side overcurrent. It's often referred to high side overcurrent, low side overcurrent, and then you'll often get an overcurrent element for the transformer neutral if you've got a grounded Y winding neutral. The high side typically trips your transformer differential lockout relay, and the low side overcurrent usually would trip just the low side relay, low side breaker, if you have one. The reason for this is it just helps you figure out where the fault was after the fact, right? If it was a downstream fault and the downstream relay failed, or even if it just miscoordinated for whatever reason, or maybe the fault was between here and the downstream relay, you tripping this low side breaker and keeping the transformer energized, that'll help them know that the transformer is healthy and they don't need to worry about that. They got to look downstream to isolate the fault. So that usually doesn't trip the transformer lockout relay, but the high side would. Because theoretically, if you have a fault over here, your low side relaying, if well set and these relays coordinate, the low side relaying should operate before here. So if the high side relay operates, that means the fault should be in the transformer, and that's why that hits the transformer differential transformer lockout relay. Yeah, okay, I think I went over that. So considerations for each type of overcurrent relay: your high voltage winding overcurrent protection. This is broken down between phase and ground, and then low side, phase, and ground. So for high side phase overcurrent protection, you may have an instantaneous overcurrent pickup. The element should be set greater than the transformer inrush. Like we just talked about, we don't want to be tripping off the transformer during inrush conditions. That's a nuisance trip, and those are bad. So we want to avoid them. That's usually like 8 to 12 times the ONAN rating of the transformer is generally what you'd set your phase instantaneous element to. Another option would be to set it greater than the maximum amount of low side fault current. So if you had a fault on the low side of the transformer and say the high side relay sees 1,000 amps for a fault right on the bushing of the low side of the transformer, if you set the pickup greater than that, then it can't misoperate for a fault that's beyond the low side relay. Sometimes you'll run into a case where you put a transformer in a weak system comparative to the transformer MVA rating. So if you did 8 to 12 times the, say 10 times the transformer MVA rating and convert that to phase current on the high side of the transformer, and that's 1,000 amps. It may be that for a low side fault, the system can't even supply 1,000 amps of fault current. And so it doesn't make sense to set a phase instantaneous element that high. That's where you want to use that 125% of a low side fault number potentially, because you can get better protection. If you set it to 10 times, then and the system's not capable of supplying that amount of fault current, you might as well just turn off your phase instantaneous element. Sometimes you may need to do that. The time over current pickup, that should be set to greater than load. IEEE, the IEEE guide on transformer protection recommends a setting that's like 125 to 150% of the transformer's maximum nameplate rating. Although higher values are sometimes used. I think CMP used to use 325% of the ONAN rating, which is, I mean, obviously that's a lower percentage of the top rating, but that's what they standardized on. I think recently they've adjusted that, and it's now closer to the value recommended by the IEEE. But then the time over current.
Can I just add too? So
Yeah.
one of the things is that we do have a transformer damage curve that all this stuff needs to coordinate with. So
Right.
You know, a lot of these percentages, and I believe Andrew's going to just address that, but just making sure that these numbers, they are going to coordinate with transformer damage.
Right. Well, right now, I usually try and break it up, right? I calculate the pickups because there are certain levels that you want it to operate for. But then when you go to select your curve and your time dial, that's what you need to compare to your transformer damage curve. Yeah. And the other upstream and downstream protection. So that's what I was just going to actually, great segue, Paul. The time over current curve and time dial, as previously demonstrated, we went over this during the Aspen one-liner class too, on how to actually coordinate a fuse and a recloser with a transformer damage curve. the high side phase overcurrent elements should coordinate with the upstream and downstream protection and protect the transformer's damage curve. This is kind of a cool note, something to keep in the back of your mind. Because of the way delta Y transformers, the currents, the phase currents relate to one another for a delta Y transformer, when you're looking to figure out what your minimum CTI is for the high side phase overcurrent versus the low side phase overcurrent, the worst case scenario is going to be for a line-to-line fault. And it just has to do with basically the low side will see that fault as a line-to-line fault, but one of the phases on the high side of the transformer is going to be the phase that has a winding that's tied to both of the faulted phases. And so that's actually going to look to that particular phase like a three-phase fault. So it looks like a three-phase fault to the high side relay, and it looks like a line-to-line fault with a lower fault current to the low side relay. And so that's going to actually shift your curves closer together. So when you're trying to coordinate high side and low side phase overcurrent elements for a delta Y transformer, you got to check those phase-to-phase faults. It's really, like we talked about during the Aspen one-liner classes, I think it's just good practice to check all different fault types in general, because sometimes the relaying doesn't behave as you'd expect. Then we have high side ground overcurrent protection. Ground overcurrent protection has different considerations than phase overcurrent due to the following factors. The transformers, depending on their winding configuration, may or may not act as a zero sequence path for or a path for zero sequence fault current to flow. We went over this ad nauseum during the last class. So that's one consideration. The ground overcurrent elements will not operate on normal balanced load. So that means you don't have to set them higher than the loadability of the transformer. You can set them a lot lower than that. Yeah, they could generally be set more sensitively. They do need to be set. They still need to be set about the maximum amount of current imbalance, and you can get inrush, like zero sequence inrush, when you're energizing your transformer too. So you want to make sure if you've got like an instantaneous ground element on a delta winding, even you need to set your instantaneous element above the inrush you might get for when you're energizing the transformer. So given these particular considerations that have to do with what type of transformer you've got, we're going to examine the ground overcurrent elements as whether or not they're connected to a delta winding or a Y winding, or protecting a delta winding or a Y winding. For delta connected windings, the instantaneous overcurrent pickup, these may or may not be used. I like to use them. If they are used, they should be set above inrush, and usually, in general, you estimate the zero sequence inrush to be about a third of the inrush we used for the phase element. So if you use 12 times the OA rating of the transformer for your phase instantaneous element and make sure that it's above that to account for inrush, you'd use like 4 times the OA rating for your ground instantaneous element pickup to make sure you're above inrush. And then beyond that, because the ground relay is looking into a delta winding, you shouldn't see any zero sequence current under any condition except for faults. So you don't really need to worry about anything else. As long as it's not going to trip for inrush, you can set it and forget it. The time overcurrent element similarly can be set sensitively because it shouldn't see any zero sequence current, as the delta winding is in a path for zero sequence current to flow. So the element will only detect ground faults that are between the relay, wherever it's connected, usually like a breaker, or it may be the bushing CTs of the transformer, but usually it's a breaker on the high side. And between those CTs and the high side windings of the transformer. A utility I'm familiar with, they set theirs quote unquote arbitrarily low. So they just say 1 amp secondary, and you can set it low and fast, and it'll detect ground faults in that small zone of protection. And then again, for the curve and time dial, you got to compare those to your upstream and downstream protection and the transformer damage curve. If your high voltage winding is a Y winding with a grounded neutral, usually you don't apply an instantaneous element in this situation, because if you can imagine, let's say this is the high voltage winding here, and this is the low voltage, that's the delta. Usually you wouldn't arrange it that way, but you understand what I'm saying. If you had a fault here, it would be very hard to differentiate between this fault and a fault that's actually in zone, right? So if you set it low enough so that, or actually worse yet, because you'd get a different fault current depending on which side of the breaker it is. What I meant to say was, it would be very, like you had another line off of here and there was a breaker, it would be very hard to differentiate between a fault here on this bus or a fault on an adjacent line. Obviously you don't want to trip for the fault on the adjacent line, but you do want to trip for a fault on the bus, or not on the bus, for a fault here. So because if you set it low enough so that it operated when you wanted it to, it would also operate when you don't want it to, is what I'm trying to say. So generally you wouldn't apply an instantaneous element. But what you can do is something called restricted earth fault. You'll also see it referred to as a 67G or an 87G. And basically what you're doing is you're looking at the neutral current and the zero sequence current. So this one's actually measured because it's tied to the transformer Y winding neutral. And then this one's based on the zero sequence current seen by 3-phase CTs. And if you compare them, it operates kind of like a transformer or a bus differential relay or a transformer differential relay. It'll only operate for faults in the zone of protection. So we're not going to go over that in detail. I don't think I've actually set, maybe once, I want to say, set a restricted earth fault element, but it is an option. Some utilities put them in everywhere. The ones that I'm familiar with here in the Northeast don't use them. Okay, low voltage winding overcurrent protection. So now heading back to phase overcurrent for low side, the low side winding. The instantaneous overcurrent for low side is, again, generally not applied for the reason we just talked about. It's difficult to differentiate between faults on the low voltage bus and the downstream feeders or lines that are leaving the low voltage bus. You will almost always have low side time overcurrent. The pickup, kind of similar to the high side, should be set above load, but you want it to be below the pickup of the high side element. And the reason for that is, if you have a fault on the low side, you want the low side relay to pick up before the high side relay. Usually you'll have a margin between the two of 25–35%. And you have to make sure you relate that to the same side of the transformer, right? Because the turns ratio of the transformer might be such that, say it's a 10-to-1 transformer, 100 amps on the low side would be only 10 amps on the high side. So you couldn't just say, well, I'll set the high side to 10 and the low side to 9. Well, that's not going to work, right? So you got to relate it to the same current base. Let's see here. Low voltage winding time over current pickup must be set lower than the high voltage winding, like I just said, in primary amps when related to the same V base. Yeah, like I just said. Okay, this comparison should also account for the transformer's LTC applicable. Yeah, typical margin is 15 to 25%. Yep. And then same thing, curve and time dial, transform, coordinate with upstream and downstream protection of the transformer's damage curve. Low voltage winding ground over current protection for Y connected windings. Same thing, generally not applied, same reason. This is all, I guess, going over the same stuff, but the time over current pickup should be, in the case of a Y winding, it should be set above the expected load imbalance. So say your load is 1,000 amps, but it's a relatively balanced circuit. Say it's a 115 kV transmission line where things are always very, very balanced. You might set that to 5% of the total load, expecting that to be the imbalance, or set it above 5%. But if you're at a distribution level where they've got, half 100 cans hung off of phase 1 and phase 2 and 3 are lightly loaded, then you're going to need to go above that. So you got to be cognizant of your application and try and consider what your maximum unbalance will be. And again, you'd like that pickup to be higher than your downstream protection pickups so that the downstream protection picks up first. Helps you coordinate your protection that way. Curve and time dial, same thing. And then if you've got ground over current protection for a delta connected winding, you can't do that very well. Because the delta winding doesn't provide any zero sequence fault current. And generally, this is going to be used in an application where the delta winding, is connected to a system that isn't grounded at all, if you were actually going to do this. So you'd have some other means of detecting ground faults, like we talked about before, where you have ground over voltage protection or something of that nature. Fused transformers, I think, did Leo cover fused transformers? He did to some extent when he did distribution protection, although that seemed to be more like, station down, and didn't really talk about the station distribution transformer.
Yeah, I don't believe he covered, he did a little bit with some of the under oil fuses, but it wasn't the focus. It was more the laterals and fusing.
Okay. You'll see a lot of fused transformers. They're generally used for transformers up to 5 MVA. So if your transformer's 5 MVA or less, it's probably just fused. From 5 to 10 MVA, it really kind of depends on the utility or the company that's putting the transformer in, the generator or whomever, how much money they want to spend. Above 10 MVA, you're going to be hard pressed to find transformers that are like, a 20 MVA fused transformer. I'm sure some are out there, but generally that's not, once you get above 10 MVA or so, you stop seeing fused transformers. The benefits of a fuse: they're cheap, they're reliable, there's little to no maintenance required for fuses. Oh, and this picture, this orange stick right here that you can kind of see, that's the actual fuse for this fuse transformer. I didn't get a very good picture of this, but this is actually the Sydney transformer. This one feeds my house. So I was jogging by there the other day and I took a picture of the transformer, but that's the fuse. I should have got a better angle of it, but there's because it's fused and there's no relaying required. There's no high side breaker. You don't need that. You don't need a control house. So this, this is like a perfect example. You got a fuse transformer, and then you got the 12 kV bus, and there are a couple of reclosers, and that's your entire station. So, excuse me, the drawbacks of a fuse is that they're slower than you generally like. Once it operates, you got to replace it. And we talked about this during one of the Aspen one-liner classes, but you can also end up single phasing customers, which isn't good. The fuses can preheat, which we're going to talk about a little bit more, but we talked about this before. If you have reclosing, so this distribution circuit, say you have faults here, every time this recloses, this fuse is getting hotter and hotter, and it's going to change the coordination interval between this fuse and the downstream recloser. You got to account for that. You can also potentially damage the fuse so that the next time it sees a through fault, it trips faster than that. I think Leo talked about that as well. And because it's just a dumb fuse, you don't get some of the other ancillary benefits that relaying provides, such as event recording and things of that nature. Fuse sizing. These are the factors that go into fuse sizing, and I'll have to apologize because I'm not an expert on this. I don't often size fuses, and when I have to, there's the clients I'm familiar with have standard fuse sizing and fuse curve shapes that they use, and they say, okay, if you have a 5 MVA transformer, you select this fuse. So, but these are the things that go into fuse sizing from the IEEE guide to transformer protection. The fuse's fault interrupting capability and the available system fault current, maximum anticipated peak load current, and the various emergency peak loads of the transformer and the transformer through fault current. So obviously you want to be above your load, right? And if you've got emergency loads like the emergency rating, long time emergency, short time emergency, and drastic action limit are usually the ones I'm familiar with. And if you the transformer through fault current, right? All those things you want to be below the through fault current. Cold load pickup. So this is when Leo must have talked about cold load. Oh, okay. All right. So you guys know what that is. The available primary system fault current and the transformer impedance, coordination with low side, source side protection, low side protection. The maximum amount of fault time on low side conductors. So if you had like a cable that came off the low side of your transformer, you might want to look at the cable damage curve. Same thing as, or not the same thing, but it's similar to a transformer damage curve. The transformer connections, this is talking about whether it's a delta or a Y, and if there's a grounding impedance, you want to consider that. Sensitivity for high impedance faults and transformer magnetizing and rush. So I know Leo covered the load size, load side fuse links. He went over this. So he was talking about how you had a upstream recloser and downstream fuses and accounting for that using the K factor. He did not cover the source side fuse link. So this is kind of the same principle. This would be more for your distribution transformer that is like the power transformer, the 5 MVA transformer that's feeding the distribution circuit. So if you had, if that was a fused transformer with a low side recloser, it's actually similar to this, but it's a different K factor. So depending on which side the fuse is, whether it's source side or load side, the K factor is different, okay? And which curve you apply the K factor to changes when it's source side or load side as well. So as Leo talked about, if you have fuses on this distribution circuit, every time this recloser recloses for a fault over here, this fuse is heating up, okay? And you want to make sure that the fuse always operates. How does that work? This one, I'm trying to remember. You apply the source side K factor. I just want to make sure I don't get this backwards. The slow curve with source side, the fast curve with load side. Yeah, okay, right. So this fuse is preheating, and you want to make sure that the recloser always trips after that fuse. But the fuse is getting hotter, so it's going to operate faster. So you need to apply that K factor to the fast curve and account for that preheating of the fuse. Okay, Leo went over this more eloquently than I did. I'm more familiar with the source side because I do this much more often than I do distribution protection. Here you apply the K factor to the slow curve, and you want to make sure that the slow curve always operates before the fuse. So there are different K factors, but it's a similar table, similar concept. It just depends on which side of the recloser the fuse is located. Blown fuse detection. So this is to prevent that single phasing that we talked about a little bit earlier, but mostly during the Aspen one-liner training. When you single phase a multi-phase customer, this can happen when there's a fault, like say a single line to ground fault on a distribution circuit outside of a fuse transformer, and one of the fuses blows. This is actually an example from the IEEE Guide to Transformer Protection. So your high side current for this fault, a B to C to ground fault, your C phase may see 600, 700 amps, say. So that fuse is going to blow first because it's seeing the most current. And your B to C current is here. These are the faulted phases. Okay. Once the C phase on the high side opens up, obviously it's not going to see any current, but because one of the phases involved in the fault is no longer a source, the A and B phase currents drop. They're cut in roughly half. Okay. And so now you may not have enough fault current to actually blow these fuses. And so now you've got two phases in, one out, and you can single phase customers. So if you have customers that are three-phase customers or whatever, the voltages that they're seeing are going to be non-ideal, say. So to account for this, you can use blown fuse detection, and there's a Schweitzer white paper on this, which is pretty interesting. And you can use the voltages that you would see, the phase-to-phase voltages you would see for a high side blown fuse for a delta Y transformer, and the phase-to-phase voltages you'd see for a fault, like in the voltage, the VT secondary that blows one of the fuses in the VT secondary. There's the characteristics of those phase-to-phase voltages are different. And so if you can compare the two, you can be sure that it was a transformer high side fuse that blew and not the VT secondary fuse that blew. And if you see this this voltage for a few seconds, then you may have single phased your customers, and then you can trip the distribution recloser to avoid voltage issues for your customers. So this is an example of that. Other types of kind of ancillary transformer protection. Geez. Oh, let's just freeze. Okay. Yeah, I'm almost done. I think we're going to be in good shape. Transformer sudden pressure relays. I think Adam might have talked about this in his one-line course, but there are sudden pressure relays, are also known as rapid pressure rise relays, that they provide kind of backup protection to a transformer differential relay. So obviously, if you have a fault inside of a transformer, you're going to cause immediate heating. The expansion of the arc is going to cause a rapid pressure rise inside the tank of the transformer. And this is an example of a sudden pressure relay. It's got a little diaphragm in there that expands on that sudden pressure, and basically it expands so quickly that it closes a contact, and then you'll usually wire that contact into a seal-in relay. This is a sudden pressure, an example of a sudden pressure seal-in relay, because obviously the diaphragm expansion is what causes the contact to close. But if that condition is held there, if the pressure stops rapidly increasing, even though it may be higher than normal, if it's not rapidly increasing, then that contact is going to open back up. So the seal-in relay detects the closure and then has a set of contacts that are maintained that can then go and trip your transformer lockout relay. Some other types of controls and alarms for power transformers. There's fan controls. These control the stages of fan cooling. Typically, you'll have a switch with on, off, or auto, and the auto contact will be in series with just a dumb thermostat, so that when the temperature in the transformer gets to be above a certain level, you turn the fans on and cool it down. A lot of times, especially with larger power transformers, you'll actually incorporate the fan cooling into your protection scheme. You'll when the transformer lockout rolls, you'll open up the fan circuit, and they call this block cooling. And the reason you do that is if you've got, if the transformer faults and it catches on fire or something, well, obviously it's going to get hot, right? So you don't want the fans will turn on, but you don't want to feed air to the fire, and you also don't want to spray flaming oil all over the place. So a lot of times you'll block cooling with your transformer lockout relay. Temperature detection, you'll usually have some form of temperature detection. It may range from just a dial that's somewhere on the tank to more complicated temperature detection. For more modern and bigger transformers, there's usually a specific device that's looking at things like the top oil temperature, the bottom oil temperature, the LTC compartment temperature, ambient temperature, winding temperatures. I'm sure I'm missing something, but the winding temperature may be measured directly. They may have like I think it's called an RTD that screws into the relay and measures the temperature of the winding, or you can calculate it. When they test the transformer, they'll do a lot of times a thermal testing. So they'll load it up, and then they'll see what the temperature of the transformer is using a thermal imaging camera. And you can then look at that and say, okay, well, under full load, the transformer got the hottest spot on the transformer, the hot spot they call it, got to this temperature. So under full load, it should be that temperature rise above ambient. And then you can calculate what the expected temperature of the winding is based on the current that's going through the CT. So that's another way of getting that if you don't have a direct measurement. Gas detection. Don't confuse this with looking at the gas that's in the tank. Like if you have a nitrogen blanket, you're not actually sampling the gas that's in the tank. What you're doing is you're sampling the oil and then looking for trace gases within the oil to look for maintenance issues. So for older transformers, they'll actually monthly or quarterly or whatever, they'll go and there'll be a little drain valve at the bottom of the transformer tank, and they'll open up the valve, take a little sample and shut it back off, and then send that to somebody to test the oil. You're looking for like acetylene, other gases, and they can indicate that the transformer winding insulation is breaking down, or it can signal that there's already arcing going on in there, that those will create those trace gases that you can test for. So Blaine, make sure you set up an oil testing routine for your new transformers that you install. LTC controls are very common for power transformers. So if your transformer has an LTC, obviously it's going to have some form of control. Somebody asked about this a couple classes ago. Why would you need an LTC who's going to stand there and move it up and down? So this is talking about that. You'll usually have a way to turn the LTC controls off. On would be like manual control right there at the mechanism housing of the transformer, or the automatic control, and that's looking at the voltage on the LTC side of the transformer and trying to keep that within band. If you're in like, you'll also often have a remote or local control switch so that dispatch can control the voltage if they want. You'll often have if you have a local control switch, that'll be paired with a raise and lower control switch, so you can actually move it up and down. Sometimes it's incorporated into the LTC controls themselves. Sometimes it's on a panel that is near the controls. And this is an example of what those controls might look like. So this 43 LR 43 is a selector switch, and then this stands for local and remote. So this contact's closed in the local state. This contact is closed in the remote state. So you, the first step in analyzing this circuit is to understand that. So you've got a local remote control. If you put it in local, then you've got an auto or manual. So again, 43 is a selector switch, M is manual, A is automatic. And so if you're in manual, then you've got another selector switch, which this can be kind of confusing. This is local remote. This is raise lower. So if you go to here, this contact will close when you want to lower it. And then this one will close when you want to raise it. So now you've got, those are your three switches that I was just describing. So you've got all the controls. If you're in local and you switch the auto manual control switch to automatic, now your LTC controller, in this case, it's a Beckwith M2001D, it can raise and lower the LTC. If you put it in a remote, now you've got maybe a relay that can raise or lower the setting, the LTC via SCADA, or put it in auto, and then again you go back and now the Beckwith M2001D is controlling it. And then yeah, this is like a backup LTC controller. So if this fails, this opens up the lower coil so that you can't lower the LTC anymore if you're under a certain voltage threshold. Same thing for raise. And then if the voltage gets too high, it'll lower the LTC for you to keep from over voltaging customers. So this is a backup in case this fails, and it's a while for somebody to get out there and fix it. And it'll prevent you from damaging customers. These are examples of the switch development for those different kinds of controls, so that you can figure out what's going on here. Paralleling controls, we won't spend a ton of time on this. This is the last slide. If you have more than one transformer in parallel, you can put in a transformer paralleling circuit. These tend to be pretty complicated schemes, but the important takeaway is the purpose. The purpose is to make the transformers operate as kind of one system instead of independently, because you can imagine that if both LTCs are operating on their own and you've got a certain band width that you're trying to maintain the voltage at, and you get above that bandwidth, then the LTCs will want to lower, right? But only one's going to lower, right? And now maybe that one changed its tap position and it lowered the voltage back into band. But now maybe the voltage goes back down and one's good. So they both want to raise, but maybe this one decides to raise. Now they're back in band, but now they're 2 steps apart, right? Maybe one's one raise and one's one lower. And now, because you've got different turns ratios for each transformer, you can get a circulating current inside the transformers. And so you've got your through current that's going to your load, but then you've got this circulating current that's just going around and around, and it's causing unnecessary loading on your transformers. It can cause them to overheat if they get out of step far enough, and they call that a runaway condition. If your time delays aren't set up right, you can also do what they call hunting. So but going back to that example where one raised or one lowered first, right? Maybe they both decide to lower, right? So they both chunk down and they lower, but because they both operated and not just one, now you're outside your bandwidth the other way. So they both say, okay, well, we better raise, and then they both raise, and then they both lower, and then they both raise. And so this is called hunting, because they're trying to meet the center of that bandwidth, but they're operating together instead of having one operate and then the other operate. So anyway, I think you guys get the point. What the paralleling circuit does is it compares the low side current for each transformer, and it ties them together in a paralleling circuit. And based on the direction of that current flow and the magnitude, the LTC controllers now know which transformer LTC should operate to keep them at the same step, and to keep that circulating current, the primary circulating current, to a minimum. And so that's what the paralleling circuit is meant to do. Usually you'll have a control switch that can change the paralleling mode from independent to parallel, so that, you know, if you had to take it out for maintenance or something, you can put it in independent and take that one transformer out, and now the transformer that's still in service can operate independently of the other one. So this is a clip from the Beckwith parallel balancing module instruction book, and kind of gives you can see where this can get complicated, but okay. And that's it. So we got about 10 minutes left. What I was aiming for, so that's good. Can answer any questions you have, either about anything really. If you guys want to talk about the homework, or if you want to talk about something I failed to cover during the class, I'm here for you guys.
Hey, Andrew, what's the difference between the ONAM rating of the transformer and the nameplate rating of the transformer?
The nameplate rating is kind of generic. The nameplate rating is like the generic term. The ONAN rating is a more specific term. So here's a transformer nameplate. Somebody says, you look at the nameplate rating, they're generally referring to the ONAN, but the nameplate has often more than one rating. Okay, so this one has 6 ratings actually. You've got the ONAN rating, which is 20 MVA at 55-degree rise. If you allow a 65-degree rise, you're allowed 22.4 MVA. If you've got one stage of cooling at 55-degree rise, you can do 26.67 MVA. You see how it's got 6 different ratings. So these would all be, you know, quote unquote nameplate ratings. The ONAN is referring to the base. It's also called the base rating of the transformer. It's under no cooling, and yeah, that's it. I don't remember what ONAN stands for. I always forget. Blaine, you remembered it last time.
Yeah. So ONAN is oil natural, air natural. So in other words,
Thank you.
as the oil heats, it naturally convects through the heat exchangers. And obviously the air just is whatever the atmosphere is. So there is, and I've seen this, I haven't seen it in real life yet, but I know there's a OFAF, which would be oil forced, air forced. So
Yep.
you could actually have a pump that pumps oil, so it actually circulates faster through the fins. So yeah, I just figured I'd mention that as well.
Yep.
But the reason why you don't see a lot of oil pumps is because if they fail, then you can't really fix it easily, and you can't run your transformer. So anything that messes with the oil, you don't see all that commonly. The only other thing, and I'm not sure if Ben was getting at this, but you do have a %Z on all these nameplates. And usually, but not always, but usually the %Z is based on the OA rating. So if you want to,
And it should specify that. So like this says 7.31%, and it gives you 20 MVA. So it should tell you what the MVA rating is that the impedance is at. But like Paul said, it's almost always the ONAN rating.
I would ask Andrew too. He's a professional settings engineer, talking a little bit about how his career has evolved, because he's only got 2 minutes, but he's pretty sharp and pretty valued in the state of Maine. So just, you know, how he came to become this expert relay settings engineer would be kind of interesting to me, but I know we only have 2 minutes, so I don't want to take up anybody's time if we're not done.
I don't know how to answer that. I mean, I think having the opportunity to work with Ron Grant early in my career was a big part of it. Especially early in my career, I worked a ton of hours. You know, Saturday morning, I used to go into the office every Saturday from like 8 to noon, and I'd get out about lunchtime. And that was what I did. And that was because I could get stuff done in the quiet, and it just felt better. So I still work more than my fair share, I would say, of hours, but I used to work a lot more of them. So a lot of hours in the years of experience I have.
And mentoring too, right? Mentoring was a big part of it. You said that working.
Yeah.
With
Oh yeah.
Grant
Ron was
mentor.
invaluable. Al Poitras too. Rest in peace. He was a great resource. And both of them used to sit right on the other side of the wall from me. And so being able to get up and say, hey, what's going on here? Like this standard says to do it this way. Why is that? And for them to have that history and that background and knowledge, especially for CMP system. And, you know, I find myself in situations now where, you know, I get asked the same question that I asked them, and now I'm passing that along, you know, and so a lot of that credit goes to them for sure. And yeah, I don't know. I don't want to brag about myself or anything. Yeah, hard work and mentorship. Yeah, there you go. That's a good way to sum it up.
Okay, any last minute questions for Andrew? Because this will be the last time we see him this semester, so. Okay, well, thank you very much, everyone. And we have some testing starting on Thursday, so take care. Have a great day, everyone.
All right, guys, good luck. Happy graduation for those of you that are.
Thanks, Andrew.
Thank
Yeah.
you.
Bye, guys.